Okay, welcome back. So this class, what we're going to do is we're going to have a small. I made a small mistake. The lecture one's video, so I want to correct it this time, and then I'm going to introduce you with process and device equations. Okay, so let's proceed. So this is what I want to correct myself. So this I have taken from the Keyside's website. Keysight is a very well-known supplier for your equipment to test the IV behavior or for characterization equipments. Okay, so from their website I have taken. You can even look at this website later. So, so what is the difference? Is modeling? They are calling it as device modeling itself. So modeling. In the modeling, we're going to have two categories. I told you there are two types of modeling, right? You guys remember, right? One is a compact modeling, right? And other one is your numerical simulation, or the key set is called it as physics-based modeling. So I think this is better way to classify them. This is a better way to classify them. So let's have this way. So device modeling, we have general, anything you model that comes in the device model. So you have two types, compact and physics-based model. So compact model, based remember the closed form expressions, right? What is closed form expressions? They're simple relations where like arithmetical operations like plus, minus, multiplication, division are allowed, and some functions like exponentials are allowed. So if you can form using them, using those criteria, it is called compact model, and they are generally for spice simulations. Okay, so spice simulations, I just want to show you one spice as well. Let me show you. So this is the LT spice, it's free. So I have taken a diode here. So whenever I take a diode, it's not diode is getting invoked. You guys have to remember this. It's not the diode. What is actually getting the thing behind this graphics, the images, the model. See, I'll show you the model. So you scroll this. So this is a spice model. So this is this IS, RS, or the parameters of the compact equation. That's getting solved when you're using this diode symbol in the spice simulators. Okay, makes sense. So this is compact model, but this is not our course. So let's go back to, yeah. So our focus is going to be on physics-based modeling and numerical simulation. In that, I'm going to classify it further. One is process physics, other is the device physics, or process simulation and device simulation. Fine. Okay. So your unit 1 and 2 is going to be, so this is your entire course. This is your course domain, entire what you're going to learn in this course, right? So unit 1 and 2, you'll be studying process model, process simulations, and you'll be learning unit 3, you'll be learning about device simulations, and unit 4 is combination of both. So you'll be building. So what is process simulation, device simulations? I'll come to that. I told you, I think I told you already in the previous introduction. So process simulation is how you going to build the device. Device simulation is how the device works. So this entire course, you'll be learning how to build devices, some simple devices, how to simulate the working of the device, and the combination of them. That's what you're going to do in this course. So I told you, power simulation is how we make the device, the equation that governs the device fabrication. Device simulation is how device works, equation that governs the device working. So you have to be very clear in this. Okay. So one more thing, a word of caution: don't confuse device simulation with device modeling. So device modeling is a general name for all the models related to the semiconductor devices. Okay. Okay. Now I'm going to introduce you the tool through which we're going to learn and apply the concepts of process models and device models. Okay, so TCAD. So TCAD comes under the category of EDA. So generally there is CAD. Even mechanical engineers, they learn CAD for fluid dynamics for different applications. Okay, so CAD is everywhere, right? So our CAD will be coming under electronics CAD. It's ECAD. We use it to design, automate electronics. So it comes in the category called EDA. So TCAD means, so already you know CAD, computer aided design. You use computers to design something. Here technology computer aided design is for specifically uh, to do process and device simulations. Okay. So I told you, right? Process TCAD for process simulation, device TCAD for device simulations. Okay, so right, process, how we make device, how the device works. Okay, that's a category here. So you can also write. Generally, we use it to meet the particular specifications. Given specifications, we will meet. We'll try to meet. We will ensure our design, or the process and the device design uh, captures the given specifications. So what I mean is, say for example, what I mean by specifications. Suppose the diode current is 100 milliampere at zero point 0.8 volt. Diode going to be have an exponential behavior at zero point 0.8 volt. They're going to be 100 milliampere. But now, circuit designer, there is a requirement for a more current. Say for example, 200 milliampere. Now, what you will be doing in the process so that the current doubles for the same voltage while it was working. So something like that. This is what I'm saying as device specification. So one way, normal ways, we can increase the doping. So there are many ways to achieve it. Okay, we'll see them. So this is what you have to be clear. So TCAD is going to be the engine through which our learning journey of process and device simulations will take place. Okay, fine. Okay, so this is again the same informations. I'm just going again, right? So in the process, uh, we we're going to see different processes, right? Our focus is going to be on diffusion and ion implantation. This two, let me take a there's a pointer. So this is going to be our focus, but we will be learning etching, oxidation, lithography, everything, right? So how to we will be learning the process, the mathematical equation associated with them. So that's why it's process TCAD or process simulations. We'll be doing the process simulations using process TCAD. And device TCAD, you'll be learning the mostly the electrical characteristics, and sometimes we'll be learning the optoelectrical characteristics of the devices. Okay. So I like to give you an example. So okay, I did the process simulations. What will be my uh, the output of the process simulations? So it should be what? It should be the device. The final device should be the output. Or one thing what you can see is how the dopant have been distributed in the device. It's called doping profile. See, this is maybe I'll show you with the next slide so that you understand better. So guys, whenever you remember the PN junction in your school days, so it will be like P type and N type getting stacked. Okay. Um, but generally, it is not so for the conventional silicon-based devices. It is for organic electronic devices or some other some other technology. There are stacks that forms PN junctions. But in conventional silicon-based technology, we generally don't have stacks to form PN junctions. Okay, so it's not like this or like this. It's not like this. Okay, so I gave you that analogy like cheese and the bread for you will understand. This analogy helps us to understand the real p junction better. Okay, we'll come to it. Okay, it's not what my thing is. What I'm trying to say is it's not just a stack. Okay, it's not just the n type and p type stack. So how exactly it happens? So you take a p type, you stack the n type. Not you take a bread, you put the cheese. It's not that way. You make p junction. So that has to be very clear. So how we make? What we do is this n type dopant will get infused into the p type, and you form this junction. You understand? It's not you put on top. It's like there'll be infusion happening. Okay, something like this. So when my question is now, when this infusion will happen? What makes this infusion happen? Just putting on them, will the infusion happen? Any other guesses? Maybe you can pause the video and can think. Uh, Now let me show you with that analogy you can understand better. See, here you can see the cheese has infused into the bread, right? And when this will happen? When you heat it, right? Same here. So we'll be heating it, which is called technically annealing. So we'll be doing annealing so that dopants enter into the p type. So the mechanism is called diffusion. That's what you're going to learn the entire unit one in very detailed way. Okay. So you will be taking this topping, and this is your final p junction, and this is a more realistic diode. And now what we saw in the previous slide is the profile. How was a dopant distributed? Okay, now tell me where the n-type dopant concentration will be very high in the p-n junction, in the realistic p-n junction, where the dopant concentration will be very high, or maybe other way. So you have cheese, you have a bread, you're heating it. Where you will find the cheesy part of the bread? The top, right? Because that's why it's entering, so that'll be more. Exactly same. So in the top, there'll be more n-type dopants and they gradually decrease. That's why there's a color gradient here. So whenever you have very bright color, that's your higher concentration. This dilute color is for lesser concentration. And that's why, see, this is your top side. This is your bottom side. So the dopant concentrations decrease this way because you have a lot of dopants here. So they are diffusing, they're entering inside. Don't worry what is diffusion, we'll be seeing in detail. So the dopant will be more here. It is as if you have a bread here, you have a cheese here. So more cheesy part of the bread will be this side, right? The top side. So this is the top side, this is the bottom side. Of course, we are seeing from left to right. So I have to be very careful in this. So okay, this is an example for a process simulation output. Electrical simulation, what do you get? Any guesses? Electrical simulations will be getting IV characteristics of the curve. One thing. So you know this very famous IV characteristics of your MOSFET. Anyway, as a part of the course, we'll be learning this. Why the IV curve looks like this. As a part of the course, we'll be learning a small amount of device physics. So you better, because that's very important for your to understand your device simulations. Okay. Okay. Why TCAD? See, generally, why not I go directly? So I told you with the TCAD, you're going to do two things. One is process TCAD, device TCAD. So suppose you want to do some device, some diode. You can go to the fab or experimental facility and randomly do something, right? You can't take some random concentration. You can't, because you have infinite choice. And fabrication takes a lot of time and money as well. It's expensive as well. So we use TCAD. Okay, so to optimize the device structures and right to pre-screen the parameters, and we use optimized parameters in the experiment. Okay, so mainly why you go for TCAD is to save time and money. Okay, so that's very important. And also sometimes used to make predictions using TCAD. Okay, when your hands-on calculations are very difficult, it's not possible, then we use TCAD. Also to get insights, how the working is happening, how the device works in very detailed way. Okay, in the real experiments, very difficult. You can't see how the electron move in a real device. You apply voltage in a PN junction, you can't see the electron movement. At least right now, we can't see them, right? But in TCAD, you can see how the electron moves, how the hole moves. So that gives you a lot of insights. And also to quickly evaluate the technological options, because I told you a lot of options will be there. So to pre-screen them, it helps. Okay. So this is some of the statements from the industries. This is from TSMC. Even though this report is a bit old, but still applicable. So a lot of industries are electronics and semiconductor industries are using TCAD. So you can see what TSMC is saying. See, they are saying like, so the companies face tough decisions to. So the companies face tough decisions to choose multitude of technological choices. So for pre-screening, they use TCAD. So to limit the number of options, right, for to experiment them, so they use TCAD. And here you can see from the Intel, it's also a bit old, but you can see the learning. See, if you use only experiment, the learning rate is this dashed line. So your learning rate is of this flow. But when you add the simulations, TCAD simulations, you have a higher learning rate. Okay, so this is your time. The x-axis is the time. The y-axis is the learning. So over the time, your learning rate is much faster. So you learn more when you add simulations with your experiments. Okay. Again, you can see here. So as I told you, it saves time and cost. Okay. So as I told you before, this